Assalamualaikum and selamat sejahtera. In this video, we will discuss the operation of three-phase, controlled, half-wave and full-wave rectifiers. These rectifiers have the same operating principle as the three-phase uncontrolled rectifiers except the drive requirement. Like other control converters, the three-phase control rectifiers need a control signal for their operation. As similar to the single-phase control rectifiers, the control signal for the three-phase control rectifiers is supplied from a single source at a specific firing angle. The effects of the firing angle can be seen in the conduction ranges of the power switches and the wave shape of voltage and current waveforms. In this discussion, we focus on the control rectifiers constructed using thyristors only. Let's start with the principal operation of a half-wave rectifier with resistive load. As shown in the box, the thyristor with the highest potential of the anode terminal will start the current conduction. However, the operation of the thyristor is initiated by a control signal injected at every commutation line. At this moment, the firing angle is equal to 0. Hence, the current location of the first control pulse is 30 degrees. To understand the effects of the firing angle, we will change the value of the firing angle within two ranges. The first range is referring to the range between the first commutation line until the blue voltage waveform is equal to 0. According to the graph, the range is equal to 30 degrees. Therefore, the first range of the firing angle is in between 0 to 30 degrees. If we consider the new firing angle is 15 degrees, thus the conduction ranges and control pulses will shift to the right by 15 degrees too. As a result, the new location of the first control pulse is 45 degrees. The second range of the firing angle is in between 30 to 120 degrees. The 120 degrees is measured from the first and second commutation lines. If the new firing angle is 60 degrees, hence the control pulses will shift to the right by 60 degrees. As a result, the conduction ranges are also shifted and the new position of the first control pulse is 90 degrees. Next, I will show a simulation work to study the effects of two ranges of firing angle toward the wave shape of voltage and current waveforms of the three-phase controlled rectifiers. For the first range, I will apply alpha equal to 15 degrees, and for the second range, alpha is equal to 60 degrees. Other than these two firing angles, I will also show you what will happen when alpha is equal to 30 degrees and 120 degrees. In this simulation, I will measure the three-phase voltage waveforms together with the control pulses, the line currents waveforms, red, yellow and blue, and lastly, the output voltage and current waveforms. In this simulation, I will start with alpha equal to 15 degrees. I will zoom the steady state waveform only. Next, let's compare these simulation results to the voltage and current waveforms of the rectifier when alpha equals to 0. From both scopes, we can see that the line currents are still DC currents. However, we can see that the line currents in the right scope are lagging the line currents in the left scope by 15 degrees, which is equal to the firing angle values. Nonetheless, we can see from the width of the current waveforms in both scopes that the conduction angle of the thyristor is remain unchanged. It is 120 degrees. Other than that, regarding the output voltage and current waveforms, we can see in both scopes that the waveforms are continuous. However, due to the wave shape of the output voltage and current waveform, we can see that the average output voltage of the rectifier with alpha equal to 15 degrees is lower than the rectifier with alpha equal to 0 degree. We will discuss the relationship between the average output voltage and the firing angle when we analyze the waveform using a mathematical approach. Next, let's see what happens when the firing angle is equal to 30 degrees. From the scope, we can see the amplitude of the output and current waveform reach 0 at certain time values. Therefore, these waveforms are not considered continuous anymore. Based on this condition, we can expect that the waveform will have a discontinuous wave shape if the firing angle is higher than 30 degrees. Let's prove the hypothesis by applying 60 degrees firing angle. According to the simulation results, the hypothesis is successfully verified since the output voltage and current waveforms have discontinuous wave shapes. Other than that, we can also see that the firing angle has shortened the conduction angle and therefore it reduces the average output voltage value. Now, let's increase the firing angle to 120 degrees. From the scope, we can see that the output voltage and current waveforms are continuous and similar to the output voltage and current waveforms when the rectifier was operating at zero firing angle. Please remember that these waveforms are also similar to the output voltage and current waveforms of a three-phase uncontrolled half-wave rectifier with resistive load. As a conclusion, to vary the average or RMS output voltage and current, the firing angle of a three-phase controlled half-wave rectifier must be higher than 0 and lower than 120 degrees. When the firing angle is less than 30 degrees, we see from the simulation results that the rectifier will work under continuous output voltage and current conditions. Meanwhile, when the firing angle is higher than 30 degrees and lower than 120 degrees, the rectifier operates at discontinuous output voltage and current conditions. Next, I will show you how to derive the equation of the average and RMS output voltages of the control half-wave rectifier. Regardless of the operating conditions of the rectifier, we will start the derivation using the general equation of both average and RMS voltages. Then, we will change the range of the integral functions according to the output voltage waveform. Based on the continuous output voltage waveform, the equation of the average and RMS output voltages can be obtained as follows. Meanwhile, since the discontinuous output voltage waveform stops at pi, hence the equation of both voltages change as follows. Please take note of the new range of the integral functions in both equations. Let's solve this example question together. From the statement, we do know that the RMS three-phase supply voltage is 400 volt and the three-phase control half-wave rectifier is supplying 10 ohm resistive load. And the average output voltage of the rectifier is 70% of the maximum average output voltage of the rectifier. Based on the statement, we need to find the value of the average output voltage before we can solve the questions. To work at maximum condition, the control rectifier must generate the same output voltage waveform as the three-phase uncontrolled rectifier. It can be achieved when the control rectifier works at zero firing angle. Hence, by using the voltage equation, the maximum average output voltage of the control rectifier is equal to this value. Eventually, we can calculate the actual average output voltage of the rectifier. Subsequently, we can use this value to determine the delay angle or the firing angle of the rectifier. However, to determine the firing angle or the delay angle, we must know the operating condition of the rectifier. It is because the equation of the average output voltage changes according to the operation condition. Initially, we assume the rectifier operates at the continuous condition. Thus, the firing angle calculated here is known as the normalized firing angle. Based on the normalized firing angle, we know that the rectifier is actually working at the discontinuous condition because the value is higher than 30 degrees. Thus, by using the actual voltage equation, the firing or delay angle of the rectifier is equal to 47.735 degrees. Next, we can calculate the efficiency or rectification ratio of the rectifier using these following calculations. And eventually, the rectification ratio of the rectifier is equal to 70.44%. Now, let's discuss the principal operation of a three-phase controlled full-wave rectifier with resistive load. As usual, a control signal will initiate the operation of the thyristors. At the top group, the thyristor with the highest potential of the anode terminal will start the current conduction. Concurrently, at the bottom group, the thyristor with the lowest potential of the cathode terminal will start the current conduction. At this moment, the firing angle is equal to 0 since each control pulse is located at every commutation lines. Therefore, the voltage and current waveforms presented by the graph are similar to the voltage and current waveforms of a three-phase uncontrolled rectifier. When the firing angle increases from 0 to 15 degrees, it will shift the conduction range to the right by 15 degrees. As a result, it changes the wave shape of the line currents and output voltage and current waveforms. Based on the output voltage waveform, we can derive the average and RMS output voltages as follows. For your information, these equations are valid for firing angles within this range only. Lastly, we will discuss the effects of large inductive loads and source inductance on the voltage and current waveforms of the three-phase controlled rectifiers. This graph shows voltage and current waveforms of three-phase uncontrolled half-wave and full-wave rectifiers with large inductive load. Due to the highly inductive load, we can see the rectifiers are supplying a constant and ripple-free output current. As a result, in the half-wave rectifier, we can see the wave shape of the line currents is the positive half cycle of a quasi-square wave. On the other hand, in the full-wave rectifier, the wave shape of the line currents is a full quasi-square wave. When we consider the firing angles in the control rectifiers, the conduction ranges will shift to the right by the angle values. Consequently, we can see the line current waveforms in both rectifiers also shifted to the right following the conduction ranges. From the graph, we can see the firing angles do not change the wave shape of the line current waveforms except the phase angle only. Hence, we can use the same approach used in the three-phase uncontrolled rectifiers to analyze the line current waveforms. However, due to the firing angles, the wave shape of the output voltage waveforms in both rectifiers change. Finally, when we include the source inductance into the rectifier circuits, we can see the same effects discussed in the uncontrolled rectifiers. At every commutation line, we can see there is a commutation interval due to the time delay of the thyristors operation and overlapping of two conduction ranges. Because of that, the wave shape of the line currents and output voltage waveforms changes at every commutation interval. By considering this range only, you can see the equivalent circuit of both rectifiers is similar to the uncontrolled rectifiers. Eventually, you can derive the equation of the commutation angle and the output voltage during the commutation interval of both control rectifiers as follows. After watching this video, make sure you compare the derivations and the equations of the commutation angle and output voltage of both three-phase controlled and uncontrolled rectifiers. I will end this video with this example question.